Well, this is the review of the 2 independent group lab using the NHIS 2013 Adult 625R dataset. Okay, so I want to run through these problems and make sure that everybody knows, and then we'll go through the questions to go with it. All right, so first of all, I have the dataset open. Let me show you our first problem. Our first problem is looking at food insecurity, and it says the problem is estimate the difference in percentage of food insecurity for all U.S. adults that have children and without children. Okay, so the 2 groups that are mentioned in the research problem are kids and no kids, and so that's our explanatory variable. Do you have children, without kids, or has kids? So the question might be, which order do you put the groups in? You can pick whichever group order you want. I like to believe that, or I like to think about how the data is actually organized. So since the data is organized that kids equals 0, which is without kids, and kids equal 1 is with kids, if Minitab defaults for the group order, then it's going to pick 0, 1. So group 1 is always the smallest alphanumerically, and group 2 is the largest. So I can kind of think of ahead and do it that way, which is why I selected group 1 is without kids and group 2 has kids. And so if you just want to keep that in mind, I'm just going to put in here some notes that kids equal 0 and kids equal 1. Okay. They're independent. They're separate groups of adults. And so our 2 populations are all U.S. adults that were without kids and all U.S. adults that were with kids. What we're interested in is food insecurity, or their food security status, and we're specifically interested in how many people are food insecure. So that means our 2 parameters are the proportion, so keyword, of the population, so that would be the first one, U.S. adults without kids, that have the event of interest, that are food insecure. So notice both these parameters end with the same event of interest, okay, that are food insecure. 95% confidence interval. I've already told you the study design is observational, and it has a random sample. Okay. All right, so the first section to deal with is to deal with the condition section. And so for this, we need to have a cross-tabulation table. So let's go into Minitab and get that for us. So in Minitab, we're going to go up to Stat, Tables, Cross-Tabulation, and chi-square. We're going to put the explanatory variable on the row. So in that case, it's kids. And we are putting the response variable on the columns, food insecure. And we're getting the counts. So that's the table that I have here in my solution key. So I want to remind you that row 0 is equal to kids 0 which is equal to without kids. Okay. And similarly, for the second one, row 1, it's kids equal 1. And that would be with kids. The other thing I want to point out is that our event of interest is column 1, which is food insecure. And so let me just kind of highlight that here for us. Okay, so now we're going to go through and answer the questions. What's group 1? So in my case, group 1 is without kids. And so there are 68 people that are food insecure that live without kids. 356 that are not. I'm sorry, 358 that are not. 54 in the other group, and 145. So remember, that's coming from this idea of looking at just these four numbers. Okay. All right, so that means since all of these numbers are greater than, since all of these numbers are greater than 10, we can assume the sampling distribution is approximately normal. Okay. All right, so that gets us to the calculation section. So let's go into Minitab and do our calculations. So it's under Stat, Basic Statistics, 2 proportions. Okay, so in this case, I can use both samples are in one column. I can do that because I know food insecurity, which is value 1, is the event that I'm interested in, and that's last alphabetically, and that the sample IDs are in the order that I put my groups in. If that's not the case, if you want to control the order of the groups, then just use summarized data, in which case you can make sample 1 what you want and sample 2 what you want. In this case, because I know the way I set it up is okay, I'm going to go ahead and do this. And so I have food insecure, because that's my response variable, and I have kids, which is my explanatory variable. I'm going to go to my options window. I'm going to do a 95% confidence interval. The hypothesized difference is always 0 in a confidence interval. The alternative sign's always not equal. And for confidence intervals, we make sure that we estimate the proportions separately. Okay? So if I say okay and okay, I get this output right here. And so let me go to my solutions key here. I'm going to tell you, first of all, that if you had used the pooled estimate of the proportion, you get this incorrect output. Okay? If you use estimate the proportion separately, you get this correct output. Now, it doesn't look like it's very different, but it is. Right? You can see the confidence interval. Confidence interval actually looks the same, right? But things like p-values, Fisher's exact test values, can all change based on that hypothesis. Okay? So we're going to use this solution here, which means that I need to be able to pick off 3 things. First thing is the point estimate. Okay, so that would be the thing that says estimate for the difference. Next, I need the 95% confidence interval. So that's the confidence interval here in the output. And so you can see that I can just cut and paste those 2 answers here. And then I calculate the margin of error. So I calculate the margin of error almost always by taking the upper confidence limit and subtracting the point estimate. So you've got to be careful. This is a negative minus a negative. Okay? So that gives me a positive 0.07897. Margins of error are always positive. Remember, we add and subtract them from the point estimate. Okay? So if you get a negative number, you've probably done a little bit of the mathematics wrong. Okay? All right, so that gets us to our conclusion section. Let's think about this conclusion section. I want to do it, first of all, by thinking about what the graph would look like. So when we're talking about 2 proportions, we're always talking about a stacked bar or side-by-side pie charts. I'm going to do the stacked bar just because it's a little bit quicker to do here. And so once again, outermost first is the explanatory variable. And so I'm going to put that the explanatory variable is kids. And then we've got food insecure. We're going to make sure that we get the options as percentages within the categories. And we're going to make sure that we omit missing data. Okay. And we can say OK. Now what we should be seeing is that, in this case, 15.9% of people without kids are food insecure, and 27.1% of people with kids are food insecure. Those are the 2 percentages we're interested in discussing. So let's kind of look at the solutions then. So in my first sentence there, I say, In this study, 426 adults reported not having children, and 68% of those were food insecure. Okay, so you're seeing the 16% and the 27.1%. So once again, those are the two percentages here that we're comparing. And so once again, those are the two percentages we're trying to see. We're comparing people with kids with people with no kids. Okay? And so once again, that's that idea of being able to pull that together. Right? The only thing I did in my graph, since you see that I have the percentages at the bottom, if you're so interested, if you go to the right mouse click and do graph options, you can say that you want the first graph, the first group at the top of the stack, and it just switches it around for you. All right, so if we're just thinking about this, right? So we now know that, let's see here, people with children are more likely to be food insecure, right? 27.1 versus 16.0. So think about what this comparison should be. When we think about the confidence interval, we should be saying something like, people that have kids are more likely to be food insecure than people without kids. So let's now take a look at the template and see if that kind of lines up here. My confidence interval is negative, negative. So I yanked out this template sentence. Okay, this is what goes with negative, negative. Okay, and so then I started filling things in. So based on this study and with 95% confidence, in 2013, for all U.S. adults aged 18 to 84, here's the P, the percentage that are food insecure. And now I'm going to compare for population 2. So that's for all adults with children. Is at least 4.1%. So I'm taking the absolute value there of the upper confidence, which is this negative number here, or at most 18.3% higher than all adults without children. Okay? So that's our inferential conclusion. It lines up with what we're thinking, right? That according to our descriptive statistics, people having children are more food insecure. Has children, more food insecure. So you want to make sure that your sentence just says the same type of thing. You want to make sure that those directional findings are in the right direction. All right? So that's question 1. Question 2. Question 2 is the hypothesis testing problem for proportions. And so in this case, we're testing if U.S. adults with a limiting health condition have a higher percentage of being uninsured than those without a limiting health condition. So once again, think about the two groups we're comparing. So in this case, it's limited versus not limited. And so once again, that's my explanatory variable. Do you have a limiting health condition? I picked them once again in order. So limited equals 0 means they have no limiting health condition. Limited equal 1 means yes, they have a limiting health condition. Once again, I set that up because I know down the line that Minitab's going to put them in that order by default. Okay, independent different groups. So we've got all U.S. adults that do not have a limiting health condition and all adults that do have a limiting health condition. The response variable is insurance status because we're interested in the event of being uninsured. And so the parameters are proportions of the populations, and notice that once again they end the same way, that have the event of interest. Okay, so now we have to test and check our hypotheses. So we're trying to figure out if the people with a limiting health condition have a higher percentage of being uninsured than those without. So let me kind of write those in words here for a second. So I'm trying to figure out if the proportion with limited is higher than the proportion without. Okay? Let me rewrite this a little bit. I know that limited equal 1 is my group 2. See? This would be limited equal 1, limited equals 0. So let me just kind of substitute here. So this would be the proportion in group 2 should be greater than the proportion in group 1. Okay, so remember, these are all our alternative hypotheses. All right, so now I need them in the order of P1 minus P2. All right, so that means I could subtract P2 from both sides, and I would get P1 minus P2. Now we're normally interested in writing it the other way, so once again, I'm just going to switch sides here. So P1 minus P2 has to be less than 0. Okay, so there's my alternative hypothesis. Okay, so think about stepping through it very carefully. Okay, once again, same observational complex random sample. Okay. All right, so condition section. First thing we need is we need to get that crosstab table. So I'm going to do that. So once again, that's still up under stat, tables, crosstab. This time, I want my explanatory variable is limited. My response variable is insurance. And I get these values. So once again, if I'm going to my table here, I'm going to remind you that first row represents people without limiting health condition. And then we have with the limiting health condition. And column 1 are my events of interest. Okay? So once again, if I go over to my number of events in group 1, it's 97. Number of events in group 2 is the 12. And then not events of interest is the other column. All of these are greater than 10. And so the conditions are met, and therefore we have an approximately normal distribution. Okay. All right, so let's do the analysis then. So Minitab, to do the analysis, it's up under Stat, Basic Statistics to Proportions. Once again, I can use my columns because of the way I set this up. And so I want uninsured as my dependent variable and limited as my independent variable. My options, if I'm doing this at a 5% significance level, then the confidence level is 95. Hypothesized difference is 0, but in this case, our alternative is less than. And then the test method says, estimate the proportions separately. That's only used for confidence interval problems. So we want to use the pooled estimate because that's what we're assuming. P1 is equal to P2. So if they're the same, why not just pool everything together? Okay? And we'll say OK. So that means that if you did it correctly, if you use the pooled estimate for the proportion, you get this green output. If you did it incorrectly and you used estimate them separately, you get this red output. In this case, the p-values are different. And so while you wouldn't come to a different conclusion, you are getting different statistics. Okay? So our test statistic, because we're using approximately normal, is that z statistic of 2.27. The p-value then is 0.988, which means that we fail to reject and cannot claim HA is true. Now let's just take a look at this for a second. So group 0, which is my no limiting condition, has a sample proportion of 0.191. And with a limiting condition, our p hat 2 is 0.103. So we were trying to prove that without a limiting condition, you were less likely to be uninsured. And it actually turns out the other way. People that have a limited health condition are less likely to be uninsured. Okay? So remember, if we're trying to prove that people with a limiting health condition have a greater chance of being uninsured, you can see that our results here go in exactly the opposite direction. People that have no limiting health condition is more likely to be uninsured. And so that's why the p-value is so large, because this data doesn't support the alternative hypothesis. All right? So we get to our conclusion section. First thing we're going to do is we're going to describe these two values. That's the results of our study. So I want a sentence that says, if you had a limiting health condition, there were 117 of you in this study. 12 of them were uninsured for a percentage of 10.3. And there were 508 that did not have a limiting health condition, of which 97 were uninsured for a proportion or a percentage of 19.1. Okay? Those are the two things you're trying to discuss and compare. And so that's the first thing you see here is my 19.1 and my 10.2. Okay? So let me slide this out so you can read the actual section here. So in this study of 508 adults reporting not having a limiting health condition, 97 were uninsured. Additionally, 117 reported having a limiting health condition, and 12, or 10.2, were uninsured. Okay? And once again, those are the two numbers you want to see in your graph, too, the 19.1 and the 10.2. So let's come back to Minitab and do a graph. Graph, stacked bar. You want to put the explanatory variable first. So in this case, we are comparing limiting health conditions, and we are looking at the response variable of uninsured. Chart options, we want to make sure we get percents within the categories, and we want to remove any missing data. And so once again, if I kind of hover over this, I see this is my 19.1, and this is my 10.3. And so I did this actually in side-by-side pie charts. Okay, so hold on a second. And you can see 19.1, 10.3. Okay. So finally, we get to the conclusion. Well, I want to remind you, you should be going up and getting the research question. And so I want to check all, right? So I could take that section there, and I could plug it down here, which is what you see. You see that based on this study and with 95% confidence, there's insufficient, so that goes with my decision rule. And now you see this phrase here as being the same that I just put together. Oh, I'm sorry, I should do it this way. I took out the limited equal 1 and the limited equal 0 and the uninsured, but I have that same phrase there. All U.S. adults with a limiting health condition have a higher percentage of uninsured than those without the limiting health condition. And I said there's insufficient evidence to say that. And I put my p-value at the end. Okay? So that's our two proportion problems. Let's talk about the mean problems next. So our first mean problem is looking at the difference in mean weight between people that are food insecure, people that are food secure and people that are food insecure. And so once again, I'm going to remind you that I set my groups up so that they were in numeric order. So this happens to be food insecure equals 0, and this would be food insecure equals 1. So once again, when you see the word between, you're certainly looking at a two-group comparison of some sort. Okay? They're independent because, once again, they're different adults. And so our populations are all adults that are food secure, all adults that are food insecure. And the response variable is weight. Okay? So our parameters then are the mean, that's the key word, weight, the variable of interest, for this population, so for all U.S. adults that are food secure and food insecure. We're doing this at 95%. Okay? So we got to go to our condition section. First thing we need to know in our condition section is what the sample sizes are. And so once again, if I'm trying to get some sample sizes here, for quantitative variables, I can go up to stat, basic statistics, display descriptives. I can pick my weight variable, and I could actually break it down by food security status or food insecure. Right? The statistics I'm interested in are the mean and the standard deviation, maybe the skewness, and certainly the sample sizes. So there's my descriptive statistics, which I just copied here up in the top. Okay. So the first thing is check if the sample sizes are large enough. So the first sample size is 461. The normality assumption is not needed. And the second sample size is 111. And once again, the normality assumption is not needed. In both cases, the central limit theorem is going to kick into play. And I'm going to be able to assume that I'm using a sampling distribution. That's a t distribution. Okay? So those two samples being large enough, step one tells me that I can use a t distribution. Okay? The next step says, can we assume equal variance and show all the work? For this case, you were asked to look at the informal way. Okay? So the informal way says take the larger standard deviation. Okay? Well, you have them here in your descriptive statistics. Larger standard deviation is the 41.62. Divided by the smaller standard deviation, which is 39.46. That's what I've got right here, equals 1.05. In this case, this is less than 2, and therefore we can assume equal variance. Just for kicks, just to show you, I decided to do the formal test as well. Okay, so if we're doing that, the formal test, we would come up under stat, basic statistics, 2 variances. We're going to pick our variable, which is weight. We're going to break it down by our explanatory variable, which is food insecure. And we're going to just say OK. And the piece that's important to us is the Levene's p-value there. Okay, so that's what I've copied over here into my solution key. And you see that since this p-value is large, if we were doing the formal test, we would be assuming equal variance. And so the last step is to figure out the degrees of freedom, and I tell you to get that from the Minitab output. So in this case, the x bar 1 minus x bar 2 is a t distribution. We're going to assume equal variances by the informal method. Okay. All right, so let's go to the calculation section then. Okay. So we're going to go up to stat, basic statistics, 2 sample t. I'm going to pick my response variable, which is weight. I'm going to pick my explanatory variable, which is food insecure. I'm going to go to my options. In my options, I want a 95% confidence interval. The hypothesized difference is 0. We always use a not equal sign. So the question is whether or not we should check this box. That's what we did in the condition section, and we decided to assume equal variances. If you don't check the box, you get unequal variances. So we'll say OK, and we get this output. So I'll show you that this is the correct output because I assumed equal variance. Here, let me zoom in here. Because I assumed equal variance, this is the output you get if you do not assume equal variance. And once again, I'm going to show you that in this case, 11.0 to 6, I'm sorry, negative 11 to 6.21. Here you get negative 10.68 to 5.89, different confidence intervals. The other thing that I want to note is if you're going to assume equal variance, you should get a line that says, here's my pooled variance. Because if they're equal, once again, I should be able to put them together. Okay? You don't have that line if you do not check the box. Right? The next thing I want to point out is that it gives you the degrees of freedom over here, 570. That's what you're going to go back and insert right here in your t distribution. So it's a t with 570 degrees of freedom. The degrees of freedom are different if you assume unequal variance. So that's an important key here. All right, so let's look at this output. First thing is, these are the descriptive statistics. Well, at least these are the descriptive statistics that you want to describe in that first sentence of your conclusion section. This is your evidence. For people that are food secure, their mean weight is 173.6 pounds. For people that are food insecure, their mean weight is 176 pounds. And so what we're trying to do now is estimate that difference. Okay? So that's going to be my first sentences in my descriptive. Okay? Let me just kind of show you that here while I've got it up and fresh in your mind. So in my conclusion section, first thing I say is the mean weight for 461 adults reported to be food secure was 173.6 pounds with a standard deviation of 39.5. Mean weight for 111 people to be food insecure was 176 pounds with a standard deviation of 41.6. Okay, so that's where that sentence comes from. It's from these descriptive statistics right here. Okay, and so in that respect, I'm going to just make sure I circle those two. That's where they're coming from. Right? Meanwhile, up here, we need to know what the point estimate is, what the confidence interval, and what the margin of error is. Point estimate for the difference is right here. It's the negative 2.4. The confidence interval is clearly right there. And then once again, margin of error, we just have to be a little bit careful. I took the upper confidence level, which is 5.89, subtracted the point estimate. Now remember, the point estimate is negative, so it's 5.89 minus a negative 2.40, which gives me a margin of error of 8.29. Okay. So that leads us to our graph. I just showed you two different ways of doing it, whether it's a box plot or whether it's a histogram. You can kind of see from the box plot that it looks like it lines up pretty well. Okay? Wouldn't be a whole lot different. Now, one thing you might want to add maybe to that, because we're comparing means and not medians, is certainly the mean symbol. So let me do that here for us. So graph, box plot with groups. I'm going to do my weight by food insecurity. I like to transpose, oops, sorry. I like to transpose mine. I'm going to make sure I omit missing data. And I'm going to go to the data view button to add the mean symbol. Now if you look at this graph, you can see that the mean symbols are practically on top of each other. Right? So there isn't a whole lot of difference here between them. All right, so let's go to our conclusion section here, our inference section. Because our confidence interval is negative positive, I yanked out this sentence. Okay? So once again, I'm just doing some replacement here. I want to remind you, population 1 is people that are food secure. So let me just put a little reminder here. Pop 1, food secure. Pop 2, food insecure. Okay, so the first sentence says, because this is negative and positive, it's unclear whether adults that are food secure or adults that are food insecure have a higher mean weight. If it's the people that are food secure, it's by, and notice it says here, if it's population 1, if it's people that are food secure, it's by at most the upper confidence limit, which is the 5.9. If it's population 2, so those would be the people that are insecure, it's by at most the absolute value of the lower confidence limit. So remember, our lower confidence limit was negative. Now I'm going to make it positive, 10.7. So writing the sentences so that we have all positive values. All right, let's move on to the confidence interval problem. I'm sorry, I meant the hypothesis testing problem for two means. So in this case, we're trying to figure out, testing if the BMI for adults that are in excellent health, I'm sorry, pH stat equal 5 is poor health. Test if the mean body mass index for people that are in poor health is greater than the mean BMI for those in excellent health. And so once again, setting up our study here, or our context section, first thing is to see what two groups we're comparing. We're comparing pH stat equal 1, which is excellent health, to pH stat equal 5, which is poor health. And once again, I put those in this order because I know that 1 would be the first group. Numerically. Okay, so our populations are all people that are in excellent health, all people that are in poor health. And our response variable then is BMI. So our parameters, the keyword is mean, variable, BMI, and then our two populations, excellent health and in poor health. Okay. We are, once again, trying to test if the people in excellent health have a lower BMI or the people that are in poor health have a greater BMI. So let me just kind of write this here. So we're trying to write So we're trying to check whether the mean for poor health is greater than the mean for excellent health. Now I'm going to stick some numbers in, so that would mean the mu for group 2 is greater than the mean for group 1. Once again, I've got to flip these around, so I'm going to get, so this is mu 2 minus mu 1 is greater than 0. But I need to get the order the correct way, in which case it's mu 1 minus mu 2 is less than 0. So just remember, if I multiply this entire equation by -1, that flips the order of the groups, but when you multiply by negative in an inequality, you flip the sign. Okay? So that's why you see down here that my hypothesis is less than. Okay? If you want to think about it a little bit differently so that you get them in the right order, right, you could also say, you could also start with the mean for excellent health should be less than the mean for poor health. Okay? All right, so that's our setup in our context section. Now we go to the condition section. Once again, we get the descriptive statistics. But before we do this, we have to subset the data set because we only want to consider 1s and 5s. And so in order to do that, we're going to go to data, split the worksheet, or subset the worksheet. We're going to do pH stat equals only 1 and 5. Just to be clear and not to destroy the original data set, I'm going to put it in a new one called BMI. Okay? So this is the worksheet I want to make sure I'm using. This is the one that's got to be active. All right? So once again, I can get my descriptive statistics. So in this case, I want BMI versus pH stat. I already picked my statistics to be the mean statistics. And I see these two sets of values. Just paying attention here. What do you think? So remember, 1 is excellent health and 5 is poor health. Do people in poor health look like, does the evidence support that they have a higher BMI? If you're looking at this, it probably does. Now the question is it beyond a reasonable doubt? Is it beyond our significance level? All right, so that's what we have to do a little bit of inference on. But let's go back to our condition section. In our condition section, First thing we have to do is check if the sample sizes are large enough. So the first one is 147. Not a problem. Normality assumption's not needed. The second one is 21, though, and so the probability plot has to be done. Okay, so I've shown you two different ways of doing a probability plot. Let me just kind of, oh, wrong way. Let me show you them here. Since, and make sure you're going to the right window again, so I'm making sure I go to the BMI window. I'm going to do graph probability plot. I've got multiple because I've got two groups. I am going to get BMI broken down by pH stat. And that would put them both on the same graph. That's okay. If you want to put that in your report, that's fine. Realize that we're only concerned about the second group, right? So the only p-value that we're actually interested in is this second one here. I want to point out that the first one is actually small. If you inadvertently looked at that, you'd go, oh, normality can't be assumed. We have a problem. But that's not the case. The sample size is large, and so the central limit theorem kicks in for us. And we don't have to worry about that. It's only when the sample sizes are small that we're concerned about that. Suppose you want to clean this up and you really only want to show pH stat equal 5. You can do that. You can go to graph, probability plot. Let's do a single one this time. We're going to pick BMI. But now we're going to go to data options and say the only ones I want to include are rows where pH stat equal 5. And you see that we get the same p-value, and now you only have one graph. You got the note on the bottom that says results include rows where pH stat equal 5. Okay. So either way will work. Just make sure you're only interpreting the ones you need to interpret. Okay. So let's come back here. So that's why I said N2 equal 21. The probability plot shows normality assumption okay. That's that idea that I want you to comment. You don't just get to stuff it up there. You got to give me a comment about it. Next question is, can we assume equal variance? Show your work. So in this case, I asked you to do the formal definition. Okay. So let's do that first. So in Minitab, we're up under Stat, Basic Statistics, 2 variances. We are now going to do BMI by pH stat, and we're going to say OK. Here's my output. My Levine's test is very small. One thing you might want to check, though, just to make sure you're using the right sheet, is that you've got the right sample sizes here, and so I can see that it's 147 and 21 up here. Okay. So my Levine's test says p-value is very small, so we're going to assume unequal variance. Because that p-value is less than 0.05, we're going to assume unequal variance. If you decided to do the informal way, which is not what I asked for, but if you had decided to do it, we could look at these 2 standard deviations up here, right? We can compare 8.49 to 4.413. So in the informal way, we'd take 8.49 divided by 4.413, and we'd see it's less than it's equal to 1.92, which is less than 2. And so we would assume equal variance. This is a case where you see that we've got conflicting results, but realize in the informal way that ratio is getting quite large. 1.92 compared to 2, it's almost like we're on a borderline situation. Okay? And once again, if you end up doing both of them, the results you should take are the ones from the formal test. Okay, so we'll get our degrees of freedom from the Minitab output. In this case, I know that our sampling distribution is a t. That's what we got from step 1. We're going to assume unequal variances. That's what we got from step 2. We did that by the formal method. Okay, so all we have to figure out later is the degrees of freedom. And we're going to do that once again from the Minitab output. All right, so let's do that. Stat, basic, 2 sample t. we're going to pick BMI by pH stat. We're going to go to our options. 95, hypothesized difference is 0. This time our alternative is less than. And we are not assuming equal variance, so we're leaving that unchecked. We're saying OK and OK. And we get this output here, which I've copied to my solution report right here. So this is the correct one for unequal variance. Here's the incorrect one that shows equal variance. Once again, degrees of freedom look different, the t-values look different, the p-values look different. Okay. In this case, we can see that the degrees of freedom is 21. So that's why I went back into the condition section and put that in there. In this case, the three things we're looking for are the test statistic. That would be the t-value of negative 2.19, the p-value, 0.020, and then finally, because that p-value is less than our 0.05, we're going to reject H0 and conclude HA is true. Just as a note, suppose you had put the groups in the reverse order. The only thing that you would see changed here is that under these descriptive statistics, which, by the way, again, are the ones we want to use in the conclusion section, they would be flipped. Our estimate for the difference would be the inverse, so it would be 4.13, and our t-value would be 2.19. Okay? But realize if you flip the groups, you're going to flip that hypothesis sign from a less than to a greater than. Your p-value is going to come out exactly the same no matter which way you do the groups. Okay? So once again, these are my descriptive statistics for my first set of sentences. And so if you see my conclusion section here, that I'm talking about the mean, should say BMI, for 147 reported to be in excellent health is 25.8, standard deviation of 4.4, the mean BMI for 111 is 30 with a standard deviation of 8.41. I think this is a typo as well, so let me fix that up. That would be 11 adults. I'm sorry, I can read. It's 21 adults. Okay. So descriptive statistics. I'm going to assume you can do the box plot. And so the inference comes up here again. And so once again, let's go back up to here and get our claim. So mean body, blah, 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 blah. I'm going to take that down here. I'm going to show you that based on this study, we decided there was sufficient evidence. And now you see this whole section that I just copied down here. Mean body mass index for all U.S. adults aged 18 to 84 that are in poor health is greater than the mean BMI for all those in excellent health. And then I just added the p-value to the end of the sentence. Okay? So we're using that research question to help us form a correctly worded conclusion section. Okay, so now let's look at the median problem. First one is a confidence interval. We want to estimate the difference between people that are above and below poverty status. Once again, that's how I set up my two groups. All right, so this is below POV equals 0 and below POV equal 1. Once again, knowing that Minitab by default is going to do in 0-1 order. Okay. Independent, different people. So all adults that live below, all adults, that live above, that's the first group, and all adults that live below, that's my second group. We're looking at age, and so now it's the median age for the population and the median age for the second population. Confidence interval 95%. In the condition section, it says, just talk about the graph in the conclusion section. So let's do that. Now I want to remind you, you want to make sure that you make the entire data set the active data set to start with. So I'm going back to my original data set. which is here. Okay. So I want to graph a box plot with groups of age with, oh, I'm sorry, it's called HP, based on below poverty. Once again, I typically transpose mine, but we also want to make sure that we get rid of any missing data, which we have. Okay, remember, data options loves to remember things that you did. Okay, if you want to put the mean symbol in, you can do it here. And I'll say OK. So if I'm looking at this problem, and I'm thinking about the shapes, I'm really thinking about symmetry. I'm not really worried about where the medians are or the means are. Those are different questions. I'm interested in shape. I would say that the top graph there looks pretty symmetric. The bottom graph may be slightly right skewed because of that longer tail on the positive end of things. Okay? So in this case, I would probably argue that these graphs have similar shapes. Okay? So if I'm thinking about my condition section, I would have said the shapes are similar and nearly symmetric. See the graph in the conclusion section, and therefore we're going to use the Wilcoxon-Mann-Whitney test. You know, you could have done some descriptive statistics. You would have seen that the skewness in both cases are very small, close to 0. Once again, the skewness is what we're thinking about. The symmetry is what we're thinking about. Okay? It doesn't matter. If you decided that the shapes were dissimilar, we're still going to go ahead and use the Wilcoxon-Mann-Whitney. We're just going to know that it is robust to violations. Okay? All right, so back in the Minitab, we want to do the Wilcoxon test. So that's under Stat, non-parametrics, Mann-Whitney. But the first thing I have to point out is it wants the data unstacked. Okay, so you have to unstack the data first. So let's do that. So it's data, unstack the columns. The first one is the response variable, so I want to unstack age by whether or not they are below the poverty level. And just to keep things clean, I'm actually going to put it in a new worksheet called age. So realize I got two columns here. I've got age 0 and age 1. Now it might be nicer to maybe think about this. So this is the age for people that are above poverty. Just to remind you. And this is the age for people that are below poverty. Sometimes I think that helps when you're looking at problems. Now notice with these two groups, you can put them in any order you want. Right? So if you had decided you wanted below poverty to be the first group, you could do that. We're going to go to Stat. Excuse me. Non-parametrics. We're going to do the Mann-Whitney. We're going to pick the order we want. Mine is above poverty versus below poverty. Confidence level, 95%. Alternative is always not equal when we're doing a confidence interval, and we'll say OK. And we get this output here. Okay? So I've got that in my solutions. Actually, I didn't change the variable names when I did my problem, but you can certainly see that I'm going to remind you these are the people above poverty and below poverty. Maybe another way of thinking about it is how many would you expect more people above poverty or below poverty? In the U.S., we have more people above the poverty line, which isn't surprising that this sample size is larger than the second one. All right, so in this study, people that are above the poverty line age at 51 years, and people that are below poverty level age at a median of 42 years. Okay? So it's that idea of trying to figure out this study and whether it's conclusive or not. And so you can see, first of all, that the point estimate is our 8.0. Confidence interval, 4 to 10.999, and margin of error is not applicable for median problems. Okay? But remember that these are the statistics I want to talk about in the conclusion section. Now, I want to talk about it with the IQR, which is quite honestly why I wrote and got those up here. Okay? Because you need a measure of spread as well. So down here in my conclusion section, the first thing you see is that in this study, the median age for 445 adults reported to be living above poverty was 51 with an IQR. Median age for 116 adults living below the poverty threshold was 42 with an IQR of 32. Okay. Next thing I want to point out is that my confidence interval is all positive. Okay. So we did our graphs. So I want to do the positive interpretation. So I start out with, based on this study, with 95% confidence in 2013 for adults aged 18 to 84, the median age, so this actually should be a mu, I'm sorry, an eta. The eta here is the median age. Population 1 is all adults living above the poverty level, is at least, use the lower confidence limit, 4 years, or at most, use the upper confidence limit, 10 years, higher than population 2. So this is our conclusion. It's consistent with what we're seeing in the graph. People that live above the poverty level tend to be older than people below the poverty level. Another way to think about that is people below the poverty level are younger than people that are above the poverty level. Okay. All right, so let's do the last problem then. Last problem is a hypothesis test involving the median. And in this case, we're looking at height and race. Okay? So test if the median height of all black U.S. adults is greater than the median height of all non-black adults using a significance level of 5%. So the two groups we're comparing there are black equal 1 and black equal 0. Once again, I put them in numeric order when I picked my explanatory variable. So black equals 0 and black equal 1. Because once again, I was thinking, if in case Minitab picks this out, now I'm going to remind you with the median problem, it really doesn't matter because you get to pick which order you want the groups in, because that's the way you're selecting. Independent, different people. So all U.S. adults that are non-black, all U.S. adults that are black. We're looking at a response variable that's height. And so our parameters are the median height for the two populations. Once again, we're going to try and figure out which way we want this sign to go. So we're trying to check if the median height for black is greater than the median height for non-black. And once again, if I substitute and put in the groups, I've got the group 2 has a higher median than group 1. Start doing some algebra here. I would get group 1 is less than group 2. Just flipping it around. Subtracting, so we get eta 1 minus eta 2 would be less than 0. Okay, so another way of thinking this is non-white people have a median height less than black people. Okay, so that's what gives me my hypotheses down here. Once again, going to my condition section, I can either get the skewness for each of the groups, or I can do my graph, right? So let's go do a graph in Minitab. I want to make sure I'm on the right window, so I'm going to make sure I'm on the full data set here. I'm going to do a graph, box plot, in this case with groups. I'm going to do height, broken down by race, in this case black and non-black. And you see that I get this distribution. Now once again, we're thinking about shape. If I'm looking at the first top one, I'm saying slightly right skewed because of that longer tail. If I'm looking at the bottom one, I'm going pretty close to symmetric. Okay. I'm going to put this graph, I'm going to clean it up and put that graph in my conclusion section. So let me just show you that it's there. And I'm going to come back up here to my condition section, and I'm going to say, in this case, the shapes are similar and nearly symmetric. I can confirm that by looking at skew statistics up here. I remind the reader to look in the conclusion section, and I'm going to use the Wilcoxon-Mann-Whitney test. Okay. So let's do that. Oh yeah, but for the Wilcoxon-Mann-Whitney, we need to make sure the data's unstacked. So that means we have to go back to that data set and unstack the data. So data, unstack columns. In this case, we're unstacking height by the variable black. I'm going to put it in a new worksheet to keep us straight, and I'm going to call it height. And just to remind you, I'm going to rename these for us. This is the height of non-black, and this is the height of black. A little bit simpler in terms of getting that for us. So now I'm going to do my statistics. So stat, non-parametrics, Mann-Whitney. I want to make sure I pick them in the right order, non-black and black. I am doing a hypothesis test, and I know that I want the sign to be less than, and I will say OK. You know what? Before I do that, let's kind of look at that graph again. What do you think? You see the two median lines. Do you think that there might be some evidence that all black adults have a higher median height than all non-black? It looks, at least in our sample, that it suggests this. Right? So let me look at our test then. So here's our results. I was just showing you the difference between the two groups here. So if you flip the groups, so I have, these are flipped. These are non-black, black. So these are the statistics I'm looking for. So the three things we want out of this is the test statistic. That's the W statistic. We want the p-value. This just shows you the two outputs depending on which group you put first. Remember that for me, I want this one. So for me, that's the correct one. Okay. And so we're looking at the test p-value for adjusted for ties, 0.0482. And so therefore, we can reject the null and claim the alternative is true. Okay. So once again, in my conclusion section, I want to be able to describe this data here. So that's what I have. There's my median and interquartile range for the two groups. You have my graph. And now, once again, I'm going to grab that sentence. Based on this study, there's sufficient evidence to claim the median height of all black U.S. adults is greater than the median height of all non-black U.S. adults with that p-value.